viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani from Department of Computer Science, Aribet College, University of Delhi. So in our previous lectures we have covered the basics of counting method, which is a technique of amortized analysis among the three available techniques, and in our other previous lectures we have also seen aggregate method. So after explaining the basics of accounting method, today let us learn about one particular example. We will take one example and see how accounting method is being performed for amortized analysis in that example. So with a quick recap of amortized analysis and with a quick recap of accounting method, here is my today's talk. So in amortized analysis we have seen that each operation is assigned a charge, and some operations can be charged more or some are charged less than their actual cost, and this charge is basically nothing but amortized cost. If an operation's amortized cost exceeds its total actual cost, we assign the difference, and that difference is known as credit, to specific objects in the data structure. So whatever credit we are left with, that is associated with specific objects in the data structure, and in case we have our credit remaining with us, then that credit can be used later in order to pay for other operations whose amortized cost we have charged less. So that means there will be some operations whose amortized cost is less than the actual cost, some will be there whose amortized cost will be more than their actual cost. So whose amortized cost will be more than the actual cost, they will deposit the credit, and the operations which are having amortized cost less than the actual cost, they will use up that particular credit. So credit, but the condition here is credit can never be negative in any sequence of operations. For a particular sequence of operations if we are considering, then credit should not be negative. And amortized cost of an operation in this way, if we can see, is nothing but an actual split between the actual cost of the operation and the credit. Now that credit could be either deposited or the deposited credit could be used up, but this amortized cost is going to be a blend of two components. One is credit, either positive or negative, and another one is operations actual cost. And here also, unlike aggregate method, each operation can have a different amortized cost, and choosing the amortized cost for each and every operation is very important. Now why this is very important? Because first of all, this cost for one particular operation will not change over the whole sequence. That means if we are talking about one particular operation, let's say operation X, and we have assigned let us say a unit of charge or a unit of amortized cost for that X operation, for every time this X operation will occur, the amortized cost will be a units. We cannot say X when occur first time it is going to be a units, and X when occur next time it is going to be a prime unit. It is not going to be. So we cannot change the amortized cost in between. So it has become more or the more important to choose our amortized cost carefully, because the cost must always be same for a given operation, no matter what is the sequence of operations. So we cannot change this in between, we can say. And then to understand this concept, that how a particular kind of amortized cost is sufficient enough, or will it work or not, let us consider an example. So here the example which we are considering is about an extensible array, which is kind of if we see the implementation level details, we can say an array list or vector in Java is implemented as an extensible array, and that array is, let's say, storing for the sake of simplicity we can say that array is storing integers. Now this array list or vectors in Java are implemented in terms of these non-extensible arrays, but here we have somewhat kind of different scenario. Here we can say we can have extensible array. Extensible array in the sense what actually this extensible array is mean, I am explaining in a moment. So here each add operation inserts a new element after all the elements previously inserted. So let us say we have 5 elements inserted and we are having one more add operation. That add operation is going to insert a new element, which is the 6th element, after all the previously inserted elements in the table. But what if there are no empty cells left? Here comes the concept of extensibility, which I was trying to explain. So if there are no cells left, a new array of integers is allocated. All the data from the old array is we can say copied to the corresponding entries in the new array, and the size of that particular new array will be double the size of the previous old array. So if there are empty cells left, the element will be inserted after all the elements which are present there, and if there are no cells left, we will allocate a new array which is going to be double the size of the previous one, and we will copy all the data from old array in the corresponding entries in the new array, and then that old array will be, we can say deleted or demolished for kind of utilization of memory. So this is the idea behind extensible array. Whenever we say an extensible array, either we are using either we are creating it at the runtime, or we are having this kind of a strategy in which after filling all the empty cells, we will allocate one more array of double the size of the previous one and copy the old entries into there. Now here if we can see in the figure, let us say we started with one particular array which is having initially it was not having any element, and then we have assigned one array or one not one array but one element of the array, which we can say one cell, and the figure is shown on the screen. So we have one cell array and we have inserted, let us say 11. Now that is the one cell array which we are having. If we are trying to have another element into that array, we do not have the space. So here if we do not have the space, what do we need to do? We need to create a new array. That means at the second step a new array is being created and the element 11 from the previous array is being copied to the new array, and the new element which is to be inserted, let us say 12, is being inserted into that array. But now the array is full. So initially the array size was 1, then after getting that array filled, we have allocated a new array which is double the size of the previous array, which is 2. So now 2 elements into that 11 and 12. And now let us say this next step says I want to insert 13, again no space. So that means a new array will be created double the size of previous, that is 2 multiplied by 2 is 4, and then we will copy elements 11 and 12 from the previous array, and then we will insert 13. So 11 and 12 will be copied in the new array of 4 elements, 13 will be inserted. At the time of inserting 14, one space is left, 14 is inserted, and if we want to insert 15 again, we do not have a space. That means here again we need to reallocate the array and the size of the newly allocated array will be double of the previous size. So, earlier size was 4 and now we have element size of the array as 8. So, if you can see, if we want to insert 15, we have 11, 12, 13, 14 copied from the previous array and then 15 is inserted into the newly array. So, if you can see the series of this insertion, what is actually happening at the step number 2, step number 3 and step number 5. At step number 2, my array is being doubled from 1 to 2. At step number 3, the array is being doubled from 2 to 4, and at step number 5, I can say the array is again doubled from 4 to 8. So, step number 2, step number 3 and step number 5 are somewhat, we can say, remarkable or different steps here, or we can also say that if we consider the insert operation here at the second step, at the third step and at the fifth step, this insert operation is actually expensive. Why this is expensive? Because this is, one way inserting one element in the newly allocated array, but this is also transferring all the previous elements from the previous array into the newer one. So, this is what we can say as an extensible array is. Now, let us try to perform accounting method or accounting amortized analysis using accounting technique on this extensible array. So, this table is getting up double in second, third and fifth step, and each normal insertion we can say is taking order n time, which is a worst case operation, and the simple analysis is going to yield a bound of order n square time for n insertions. So, one insertion is taking order n time, that is the worst case analysis, and obviously, if we are talking about n insertions, then this is going to give me a bound of order n square time. So, again this actually analysis which we have given in terms of order n square is actually an upper bound analysis, is a correct analysis, but it is not the tight analysis. So, now what are we going to do in terms of accounting method? So, I am saying that we are going to charge 3 units for particular for each and every insertion. We are going to charge 3 units. Now, the first question which comes to my mind, why I am talking about charging 3 units? Isn't it charge of 1 unit sufficient or charge of 2 units is sufficient? Now, see what is happening here. Let us say we cost 1 unit. It is now it is a well known fact that a normal insertion, or we can say actual cost of one normal insertion is 1 unit. That's an order 1 operation. So, we say it cost 1 unit to insert an element, that is very clear. Now, and again we also say that 1 unit is required to move it when the table is doubled, because that element has to be moved from the old table to the new table. So, for that movement 1 unit is also required. Now, can we say that 1 unit per insertion charge is enough? Looking at the cost of movement, we can easily conclude that no, because if we charge 1 unit per insertion, there will be nothing left over to pay for the movement of this element into the next one. That is fine. So, what about if we fix a charge of 2 units per insertion? Is it going to be sufficient? No. The charge of 2 units per insertion is again not enough, not sufficient. Instead, we need a charge of 3. Now, why do we need a charge of 3? Let us try to understand. Now, here on the screen, if you can see, we have one table in which there are rows where the first row is I is the number of operation, ith operation if we say, then SI is the size of the table in terms of elements, then CI is the actual cost which is being incurred in insertion, in performing that particular ith insertion. Coming to CI prime is the amortized cost which is being charged from the insertion operation in this process. And we have one more row which is BI. Now, BI is very important row here, which say that BI is the balance after ith insertion. Now, see what is happening here. If we can see we have simple 1 2 3 4 ith operation. Then if we have SI is the size. So, for first insertion the size was 1. At the second step, if you can recall, the size was doubled, so it become 2. At the third step, it also become doubled again, so from 2 it becomes 4. At fourth step it was 4, and after 4 insertion, if we want to insert fifth element, there was no space and then it was doubled. So, for 5 6 7 the size was 8, even for the 8th element the size was 8. If we want to insert 9th element, we do not have a space, we need to double it. So, at the position at the operation number 2, at the operation number 3, 5 and 9, the size is being doubled, and that is what is being written in the column SI, the row SI. Now, if we come to CI prime, so CI prime, if you can see, is the amortized cost for all the insertion operation. Please notice this row CI prime. This CI prime is having 3 for every operation, and yes, this is what we have charged is 3. Now, coming to CI, which is the actual cost. Looking at the actual cost, we need to perform some kind of, we can say, some simple calculations. If we consider first operation, we are giving only one insertion, only one, but at the second step one element is being inserted, another element is being moved. So, the cost is 2, not 1. At the third step, one element is being inserted, 2 elements are being moved from the previous table. So, the total cost is 2 for movement, 1 for insertion is 3. At the fourth, it is trivial, only one element being inserted, but at the fifth operation again, if you can see SI has been doubled. SI has been doubled, that means 4 elements from the previous table have been moved into the new table. So, cost of 4 units for that plus cost of 1 unit for insertion. So, the total cost is 5. Again for 6, 7, 8 it is trivial insertion, so only 1, 1, 1, and at the 9th position, when the array size has been doubled, 8 elements have been moved and 1 has been inserted, so 9 elements. So, if you can notice the relation or correlation between SI and CI, we can say CI is different at every point of time when SI is being doubled, because then that actual cost is we can say is a component which is including the cost of moving previous elements plus the cost of insertion also. Now, coming to BI, the very important thing which is balanced after the ith insertion. Now, here if we can see, we have after the first insertion we have charged 3, but the actual cost was 1, we are having a balance of 2. At the second step, we have again charged 3 and the 2 was balance. So, total credit becomes 5. Out of that 5, 2 units have been used up as the actual cost, and what is being remaining is 3. Again 3 remaining in the credit and 3 charged for the third operation, we have total 6, and and out of that 6, 3 have been used up as the actual CI and we have 3 left. So, this is what is happening. So, with that 3 left, we have 3 more in the account with the fourth insertion, but the fourth insertion is trivial, it is not ending up in doubling the size. So, only 1 unit has been kind of we can say is spent, and out of that 6, 1 is spent, 5 is remaining. Then this 5 is remaining, and then we can say again charged 3 units for the fifth element. So, 5 plus 3, we will be having 8 units of credit, and this 8 units of credit, out of which 5 will be spent in as the actual cost, because here doubling of array has been involved. So, 5 is the actual cost out of 8, and the balance after insertion is 3. So, here if you can see the amount BI, that is having 2, 3, 3, 5, 3, that means sufficient credit we can say have been maintained. Now, let us say if we try to see what happens if we are charging only 2 units, because the first intuitive thing which comes into our mind is 1 unit for kind of insertion, 1 unit for moving that element into the next array, 2 unit would be sufficient. Now, see what is happening. If we charge 2 unit, so first element have been charged 2 unit, one of which is being spent in insertion, one is in the balance. Now, the second insertion is again being charged 2 units. So, the total credit here till this point is 2 plus 1 is 3, and we have spent 1 into insertion of that particular element. So, after that insertion, it is not only the insertion of one element has been moved, because at the second step itself the size has been doubled. So, amount which has been used up from that 3 units will be 2 units, and we will be left with only 1 unit. Now, at the third step, when we want to double the size again, we have 2 elements to be moved to the new table, while the credit which we have is only 1. That is the problem here. So, this is the scenario if we are saying that 2 units are being charged enough, are being charged, they are not enough. This is why they are not enough, because even at with a simple trivial statement or the simple trivial situation of 3 units, 3 insertions, we have seen that we are not able to perform the movement from the second step to the third step because of we can say lack of charges. So, here we have to have 3 units per insertion, 3 unit charge for per insertion. So, in order to generalize, if we can see, we can say M is referring to the mth element which is being inserted. How these 3 units are spent? One unit is used to insert the M immediately into the table. Obviously, 1 unit is required for insertion. Then 1 unit is moved. 1 unit is used to move M the first time the table is grown after M is inserted. That is also very valid. When you inserted the M, and whenever the table will grow after after its insertion the first time when the table grows, 1 unit is moved, 1 unit is required to move that element M. Now, what about third unit? If you can try to generalize it, you can see 1 unit is required or 1 unit is donated to the element M minus 2 to the power kth element, where 2k is the largest power of 2 should not exceeding M, and is used to move that element the first time your table is grown up after M is inserted, and this is what I have explained with the help of step number 1, step number 2 and step number 3, and at step number 3 we have seen that our credit is not sufficient in order to move even 2 elements to the third step. So, that third unit here is required to move that element. So, third unit is donated or placed, we can say, with the element m minus 2 to the power k, where 2 to the power k is the largest power of 2 and it should not exceed m, because in that case this m minus 2 to the power k can be negative. So, there that third unit will be used. So, yes, 1 unit is not sufficient, 2 units are also not sufficient, but instead we require 3 units. So, this is the we can say example where we have seen that choosing amortized cost very carefully is important. We should not be too liberal, we should not be too conservative on assigning or in choosing the amortized cost for each and every operation. So, here by 3 units we can say whenever an element is moved, that move is already paid for. I mean, we do not have any move which is not being paid for. The first element, the first time an element is moved, it is paid for paid for by one of its own time units that was charged to that particular element when it was inserted, and all the subsequent moves are paid for by the donations from element inserted later. This you can see if we have taken the element 1, the first element we have taken 3 units have been paid, 1 for insertion and 1 for the movement of the next movement to the next table at the second step, and then at the third step the third credit or the third unit is also required. So, first time an element is moved, it is paid for its it is paid from its own charge, and all subsequent moves are paid for by the elements later inserted later. So, that we require 3 units here. So, in this lecture we have seen one particular example of accounting technique or accounting method of amortized analysis, and we have seen how important it is to assign an appropriate amortized cost, neither less nor too much, for a particular operation. If we are talking about accounting method, this assigning amortized cost is very important, and this we have seen with the help of example of extensible arrays. Hope you have enjoyed the lecture. Thank you.